Okay, let's continue our discussion of complex numbers. Today what we're going to do is we're going to look at a geometric interpretation of a complex number. So let's look at the complex number z equal to a plus I times b, and we'll remember that a and b are real numbers. So these are real numbers. Recall that the real part of z, this is equal to a, and the imaginary part of z, this is b, okay? So let's draw, in the Cartesian plane, let's draw a pair of axes perpendicular to one another, intersecting at the origin. Instead of calling this horizontal axis the x-axis, I'm going to call this the real axis. And my vertical axis over here, I'm going to call this my imaginary axis. Okay? So now I'm looking at our complex number z, and what I'm going to do, I'm going to represent that complex number as a point in the plane. And the way in which I'm going to do this is I'm going to go out along the real axis a units from the origin. Now, if a is positive, then I'm going to move in the direction to the right of the origin. And if a happens to be negative, then I'm going to move in the direction to the left of the origin. So I'm going to assume, for our purposes, that a is positive, and let's say that the distance between the origin and this point here on the real axis, we'll assume that this distance is a. Okay? And then I'm going to do the same thing with the imaginary part of z. So the imaginary part of z is equal to b, and what I'm going to do is I'm going to move b units along the imaginary axis away from the origin. If b happens to be positive, I'm going to move upward. If b happens to be negative, then I'm going to move downward. All right? And again, for our purposes, I'm going to assume that b is positive. So I'm moving b units away from the origin to this point located on the imaginary axis. And since b happens to be positive, I'm moving upward away from the origin. And now I'm going to locate this point. And this is the point z equal to a plus ib. All right? So let me draw a radial line from the origin to this point. And I'm going to complete this little triangle here. This is a right triangle because this angle here happens to be a right angle. All right. And I'm going to label this angle in here theta. And again, the way we measure these angles, we measure the angle between this radial line and the real axis, and we assume that theta is positive when we measure in the counterclockwise direction. Okay. So now what do I have? I have, because this happens to be a right triangle, I know that a is equal to the length of the hypotenuse, which is the length of the radial line from the origin to the point z, and I'm going to call this r. So the distance from the origin to the point z is r, and that's the hypotenuse of my right triangle. So a is equal to r times the cosine of theta, and b, the length of this side opposite the angle theta, b we know is equal to r times the sine of theta. So now our complex number z, which is equal to a plus ib, can also be written as follows. It can be written as r times the cosine of theta plus I times r times the sine of theta. And this in turn can be written as r times the cosine of theta plus I times the sine of theta. Okay. But what is r? So r is the length of our hypotenuse, and we have a right triangle sitting here where the side adjacent to the angle theta has length a, and the side opposite the angle theta has length b. So we know that r, the length of the hypotenuse, is going to be the square root of a squared plus b squared. And you'll remember from our last lesson that we called this quantity, the square root of a squared plus b squared, we called this the modulus of z. And we denote that by putting these absolute value signs around z. So I can write z as equal to the square root of a squared plus b squared times the cosine of theta plus I times the sine of theta. All right? Furthermore, my angle theta is equal to the inverse tangent of y divided by x. So far, so good? All right. So this representation here, and I'm going to change this back to the black ink. This representation is called the polar representation of the complex number z. Okay. So let's take a look at a polar representation of, say, a complex number z equal to, let's make it 1 plus I. Okay. So now what do I have? I have that that the real part of z, this is equal to 1, and the imaginary part of z is equal to, well, it's the coefficient on I, and that happens to be 1. So now let's locate the point z in our complex plane. So here again, this is the real axis, and this is my imaginary axis. And I'm moving out 1 unit in the positive direction along the real axis, so I'm going to say it's to this point here, and 1 unit along the imaginary axis in the positive direction, which is up from the origin, and that brings me to this point here. And so this point represents the complex number z equal to 1 plus I. And I'm going to draw this radial line here. And again, I'm going to switch this to red. So this is 1 unit, and this is 1 unit. That means that the length of my radial line from the point z to the origin is just going to be the square root of 2. Okay, so I'm looking at this angle in here. This is the angle theta. And what do I know about theta? Well, I know that theta is equal to pi over 4. Okay, so I can write z equal to 1 plus I. I can write this in polar form. So as a polar representation of the angle of the complex number z, I can write this as the square root of 2, which is the modulus of z times the cosine of pi over 4 plus I times the sine of pi over 4. Now, is this the only polar representation of the complex number z? The answer to that is no. Okay, because what I can do is I can write z is equal to the square root of 2 times the cosine of pi over 4 plus any integer multiple of 2 pi. And then plus I times the sine of pi over 4 plus any integer multiple of 2 pi. So the polar representation of a complex number is not unique. There are infinitely many polar representations for a given complex number. So these represent, these numbers represent all of the polar representations of z equal to 1 plus I. Okay, let's take a look at another one. Suppose I have, let's do this one. Suppose I have, so as a second example, z equal to minus I. All right, then the real part of z is equal to 0, and the imaginary part of z is equal to, well, it's the coefficient on I, the imaginary number I, and that coefficient in this case happens to be minus 1. So where is our complex number? Here's the real axis, and here's the imaginary axis. And my complex number z in this case equal to minus I, that's going to be located, well, 0 units from the origin along the real axis and minus 1 unit from the origin along the imaginary axis. So that's going to bring me to a point down here, and this is z equal to minus I. Right, so here's my point, z equal minus I. And now what do I have to do to get the polar form? I have to look at the angle between the radial line connecting the origin to my point z and the real axis. So I have to look at this angle here. And what is that angle equal to? Well, this is theta equal to 3 pi divided by 2. And so now what do I have? I have z equal to minus I is equal to 1. So the modulus of z is 1 times the cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. And again, this is not the only polar representation. So this is my polar representation of minus I, but it's not the only polar representation because I know we have infinitely many, and those polar representations have the form given by the cosine of 3 pi over 2 plus 2 pi k plus I times the sine of 3 pi over 2 plus 2 pi k, where k happens to be any integer. Oops. And I'm going to get rid of that equal sign there. And so these, happened here? Okay, here we go. So these are all of the polar representations of Z. Okay. All right. Let's see what happens if we have two polar representations of two complex numbers. So suppose I have Z1 is equal to R sub 1, so R sub 1 happens to be positive, times the cosine of theta sub 1 plus I times the sine of theta sub 1. So this is a polar representation of Z sub 1, and I have a second complex number, so this is Z sub 2, and it has the polar representation R sub 2 times the cosine of theta sub 2 plus I times the sine of theta sub 2. Okay. So I might have something that looks like this. So this is Z sub 1. This angle here is theta sub 1. And the distance from this point to the origin is R sub 1. And then I might have another complex number. Let me get rid of that. I don't want that one. Let's put it over here somewhere. Z sub 2. And the distance here from the point to the origin is R sub 2. And this angle here is theta sub 2. And now what I want to do is I'd like to find the polar representation of Z sub 1 times Z sub 2. So let's see what we can do with that. So I know that Z sub 1 times Z sub 2 is going to equal R sub 1 times the cosine of theta sub 1 plus I times the sine of theta sub 1 times R sub 2 times the cosine of theta sub 2 plus I times the sine of theta sub 2. Okay, and now let's multiply this out. So I have R sub 1 times R sub 2 times, and now I have the cosine of theta sub 1 plus I times the sine of theta sub 1 times the cosine of theta sub 2 plus I times the sine of theta sub 2. And I have to multiply these two quantities together. That's going to give me the cosine of theta sub 1 times the cosine of theta sub 2 plus I times the sine of theta sub 1 times the cosine of theta sub 2 plus, then it's going to be the cosine of theta sub 1 times I times the sine of theta sub 2. And then finally, I have I times the sine of theta sub 1 times I times the sine of theta sub 2. Well, I times I is negative 1, so this product is going to look like minus 1 times the sine of theta sub 1 times the sine of theta sub 2. Okay. And so this is equal to R sub 1 times R sub 2 times the quantity. So let's gather up our real terms. So this cosine theta sub 1 times cosine theta sub 2, and this term here minus the sine of theta sub 1 times the sine of theta sub 2. These are both real terms, so I'm going to group them together. And then the other two terms, they contain a factor of I. So these are going to be imaginary numbers, these two terms here. They're going to be imaginary numbers, and I'm going to write those, that sum, as I times the sine of theta sub 1 times the cosine of theta sub 2 plus the cosine of theta sub 1 times the sine of theta sub 2. Right? And now we can simplify because we have these additive identities for sine and cosine. And what can you tell me about this quantity here, the real part? Well, we know that this is equal to the cosine of theta sub 1 plus the cosine of theta sub 2. And over here, with the imaginary part, I have the sine of theta sub 1 times the cosine of theta sub 2 plus the cosine of theta sub 1 times the sine of theta sub 2. And this is equal to the sine of theta sub 1 plus theta sub 2. How about that? All right. So we have a really nice identity here where the product of z sub 1 and z sub 2, this is equal to r sub 1 times r sub 2 times the cosine of theta sub 1 plus theta sub 2 plus I times the sine of theta sub 1 plus theta sub 2. So if we go back, let's go back to our drawing. Let's go back to this drawing here. What does that tell us about the location of z sub 1 times z sub 2 in the complex plane? Well, it tells me that that's going to be located at an angle of theta sub 1 plus theta sub 2 away from the positive real axis. So if I look at this angle here, this is theta sub 1 plus theta sub 2, and then I take r sub 1 times r sub 2. So r sub 1 times r sub 2, maybe that's some value way out here. And so the location of my complex number, z sub 1 times z sub 2, is going to be along this radial line where the distance here between the origin and this point, z sub 1 times z sub 2, this distance is r sub 1 times r sub 2, okay? So if both r sub 1 and r sub 2 are greater than 1, then this product is certainly going to be greater than 1. All right. So let's look at an example. Suppose we have complex numbers z sub 1 equal to, well, let's do this example, 2 times the cosine of pi over 4 plus I times the sine of pi over 4. And z sub 2 is equal to 5 times, let's make it the cosine of pi over 6 plus I times the sine of pi over 6. Okay? Now, what I want to do is I want to find z sub 1 times z sub 2. Okay? Let's do that geometrically first. So what does our, I'm going to get rid of that. That was not a very good line. Okay, so here again, this is my real axis, and here's my imaginary axis. And z sub 1 is going to lie along here, and I'll say this is, let's make this 2 units. So the distance from here to here, that's 2 units, and this angle here is pi over 4. All right, so this point is the complex number z sub 1. And let's do this, make this blue. And then z sub 2 is going to be located along this line. This is 2, 2, we'll say it's out here. So the distance between this point and the origin, this is 5 units. And this angle in here is pi divided by 6. All right, so what do I know? I know the location of z sub 1 times z sub 2. That's going to be along a radial line that makes an angle of pi over 4 plus pi over 6 with the real axis. So we'll say that's going to be along this line. And again, maybe I'll change the color. So this angle here is pi over 4 plus pi over 6, which is equal to, what is that? That's going to be 10 pi over 24, which is equal to 5 pi divided by 12. Okay? And how far away is our complex number z sub 1 times z sub 2? How far away is that from the origin? Well, it's going to be 2 times 5 units away. So it's going to be 10 units away. So I'm going to draw it way up here. So this distance from here to here is 10 units. So here's my point, z sub 1 times z sub 2. All right, let's find it analytically. So we know that z sub 1 times z sub 2, this is going to equal r sub 1 times r sub 2, where r sub 1 is 2 and r sub 2 is 5. So this is going to be, I'm going to write it this way, 2 times 5 times the cosine of pi over 4 plus pi over 6 plus I times the sine of pi over 4 plus pi over 6. And so this gives me 10 times the cosine of 5 pi over 12 plus I, oops, there should be an I there. I times the sine of 5 pi divided by 12. So this is a polar representation. Polar representation of z sub 1 times z sub 2. But it's not the only polar representation. So we also have the polar representations 10 times the cosine of pi times 5 over 12 plus 2 pi k plus I times the sine of 5 pi over 12 plus 2 pi k. So this is all. So these numbers here, k can be any integer. K is an integer, any integer. So these numbers represent all polar representations of z sub 1 times z sub 2. Questions on any of this? Okay, if you have questions, you should post your questions on the bulletin board, and your instructor will get back to you with an answer. All right, this technique can be generalized. So we're going to look at the following generalization, suppose I have a complex number z equal to r sub 1 times the cosine of theta plus I times the sine of theta. Let's see. This is cosine, cosine theta. Okay, and what I want to do is I'm going to let n. So this n here is a positive integer. Okay. Then I'm going to look at z sub 1 to the n power. So this is equal to r sub 1 times the cosine of theta plus I times the sine of theta raised to the n power. And this in turn is equal to r sub 1 to the n power times the cosine of theta plus I times the sine of theta to the n power. Now, here's what we're doing. So I'm taking, here's theta, here's z, and if I take z squared, so I'm going to look at z squared, where's that located? Well, it's going to be located along a radial line that makes an angle of 2 theta with the real axis. Okay, and if I look at z cubed, so again, here's theta, and here's my z, and now I'm looking at z cubed. So what is that? That's going to be z times z times z, which means that what I'm doing is I'm looking at z cubed, and that's going to be along a radial line. That's going to be a point on a radial line that makes an angle of 3 theta with the real axis. And if I continue this pattern, then z to the n power. So here's z. This is theta. So here's z equal, let's say the cosine of theta plus I times the sine of theta. And if I look at z to the n power, then what I'm doing is I'm taking, this is 2 theta, this would be 3 theta, here would be 4 theta, and I'd keep on doing this, adding these up, until I get to, say, n theta. And my z to the n is going to be a point on this radial line that makes an angle of n times theta with the real axis. So my z to the n is just going to be, in this case, it's going to be r to the n. I should have an r up here. R to the n times the cosine of n theta plus I times the sine of n theta. So in general, again, just to reiterate, if I have z is equal to r times the cosine of theta plus I times the sine of theta, then z to the n power is going to equal r to the n times the cosine of n theta plus I times the sine of n theta. So if I have z is equal to, let's make it 3 times the cosine of pi over 6 plus I times the sine of pi over 6. And I look at z to the 4th power. This is equal to 3 to the 4th power times the cosine of pi over 6 times 4 plus I times the sine of pi over 6 times 4. So this would be 81 times the cosine of 2 pi divided by 3 plus I times the sine of 2 pi divided by 3. So this gives me a polar representation of z to the 4th power. But we also know that there are infinitely many polar representations, and the set or the family of all polar representations is given by 81 times the cosine of 2 pi divided by 3 plus 2 pi k plus I times the sine of 2 pi divided by 3 plus 2 pi k. Okay? Not so bad. Now let's look at one other thing. Let's look at this. Suppose I have z is equal to r times the cosine of theta plus I times the sine of theta. And what I want to do is I want to look at the nth root of z, which I denote by z to the 1 over n power. So this is the nth root of z. This is a lot like with real numbers. If I had, let's say, the 4th root of 81, this is just equal to 3. So this is the 4th root of 81. Just as a reminder of how these roots are denoted. Now, I'm going to set w. I'm going to set w equal to the complex number that represents z, the nth root of z to the 1 over n power. So w is the nth root. Whoops. And I have to put that on. Nth root of z. And here I have to be a little bit careful because I'm saying the nth root of z, but in point of fact, we're going to find that there are a number of nth roots of z. So I should really have here a nth root of z. Well, what does that mean? That means that w to the n power is equal to z. Okay, so if z is an nth root of z, then w to the n power is equal to z. Okay, so now let w have the polar representation. I'm going to say w has the polar representation. Let's call it r sub 1 times the cosine of theta sub 1 plus I times the sine of theta sub 1. All right, then w to the nth power is equal to r sub 1 to the nth power times the cosine of n times theta sub 1 plus I times the sine of n times theta sub 1. And we want that. So we want this quantity to equal r. We want this quantity to equal, let me do it this way. We want this quantity to equal z, which is equal to r times the cosine of theta plus I times the sine of theta. So now let's compare. So what does this mean? This means that r sub 1 to the nth power has to equal r. So r sub 1 to the nth power has to equal r, which implies that r sub 1 is equal to the nth root of r. And I can always take the nth root of r because r happens to be a non-negative number. Okay. Why is r a non-negative number? Because r is the modulus of z, and the modulus is always non-negative. And then here we have the cosine of theta has to equal the cosine of n theta sub 1. So we have to have that n times theta sub 1 is equal to theta. And this implies that theta sub 1 is equal to theta divided by n. So far, so good? Okay, so here's what we have. If we have a complex number z equal to r times the cosine of theta plus I times the sine of theta, then an nth root of z is given by r to the 1 over n power, the nth root of r, times the cosine of theta to the n divided by n, plus I times the sine of theta divided by n. Now, here's how we get more nth roots of a complex number. So z, we said z is equal to r times the cosine of theta plus I times the sine of theta. This is one polar representation of the complex number z. Remember, we said there are infinitely many, and those other polar representations are given by r times the cosine of theta plus 2 pi k plus I times the sine of theta plus 2 pi k. So if I'm looking at the nth root of z, and I have a polar representation of z in this form, r times the cosine of theta plus 2 pi k plus I times the sine of theta plus 2 pi k, where k happens to be an integer, then the nth root of z is going to be r to the 1 over n power times the cosine of theta plus 2 pi k divided by n plus I times the sine of theta plus 2 pi k divided by n. And now here, k can take on the values 0, 1, 2, all the way up to n minus 1. And then when k hits n, we pick up another multiple of 2 pi. So what we have is the following. We have that given a complex number z, if we're looking at the nth root of z, there are n distinct nth roots. Okay, so let's look at an example of this. Let's see what we can do with the following. We'll take z is equal to 81 times the cosine of pi over, let's make it pi over 3, plus I times the sine of pi over 3. And now what I want to do is I want to look at the nth root of z. Now there should be, I'm sorry, let's make that specific. I'm going to look at the fourth root. So this is the fourth root of z. Now there should be 4 distinct fourth roots of z, and so we want to find them all. So we want to find all of them. Okay. Well, what I'm going to do is I'm going to represent z as 81 times the cosine of pi over 3 plus 2 pi k plus I times the sine of pi over 3 plus 2 pi k. So these are all the polar representations of z. K can be any integer. Then the nth root of z is going to be the fourth root. This is the second time I did that. The fourth root of z is going to be the fourth root of 81 times the cosine of pi over 3 plus 2 pi k divided by 4 plus I times the sine of pi over 3 plus 2 pi k divided by 4. So this is equal to 3. So the fourth root of 81 is 3 times the cosine of pi divided by 12 plus 2 pi k divided by 4 plus I times the sine of pi divided by 12 plus 2 pi k divided by 4. And k now can be any integer. So what I'm going to do is I'm going to set k equal to 0, 1, 2, 3, and 4. And see what happens. So I get the following. I get z to the 1/4 is equal to 3 times the cosine of pi over 12. And k is equal to 0, so this is just going to be the cosine of pi over 12 plus I times the sine of pi over 12. So this is when k is equal to 0. The fourth root of z is also equal to 3 times the cosine of pi over 12 plus, now here I'm going to set k equal to 1, and when k is equal to 1, this gives me pi over 2 here, plus I times the sine of pi over 12 plus pi over 2, and I can write this as 3 times the cosine of 7 pi divided by 12 plus I times the sine of 7 pi divided by 12. All right. Well, this is a different root of a different fourth root of z distinct from this one up here, because the angle that this complex number makes with the real axis is 7 pi divided by 12, and that's certainly different from this complex number where the angle that it makes with the real axis is just pi divided by 12. Let's continue. So we're still looking for fourth roots of z. This is going to be 3 times the cosine of pi divided by 12 plus 2 pi times 2 divided by 4 plus I times the sine of pi over 12 plus 2 pi times 2 divided by 4. Why the 2 here and here? Because we're setting k equal to 2 now. So we're looking at the case, here we looked at the case where k is equal to 0, here we looked at the case where k is equal to 1, now we're looking at the case where k is equal to 2. And so this is equal to 3 times the cosine of pi over 12 plus pi plus I times the sine of pi over 12 plus pi, which we can write as 3 times the cosine of 13 pi over 12 plus I times the sine of 13 pi divided by 12. And again, this is when k is equal to 2. Now let's look at k equal to 3. So in that case, the fourth root is going to have the form 3 times the cosine of pi over 12 plus 2 pi times 3 divided by 4. plus I times the sine of pi over 12 plus 2 pi times 3 divided by 4. And so this gives us 3 times the cosine of pi over 12 plus, so this is going to be 18 pi over 12 plus I times the sine of pi over 12 plus 18 pi over 12. And this is equal to 3 times the cosine of 19 pi over 12 plus I times the sine of 19 pi divided by 12. Okay, so I have 1, 2, 3, 4 distinct complex numbers which represent the fourth root of our complex number z. Okay. What happens? So now what happens when k is equal to 4? Well, in that case, I'm looking at the fourth root of z. That's going to be 3 times the cosine of pi over 12 plus 2 pi times 4 divided by 4 plus I times the sine of pi over 12 plus 2 pi times 4 divided by 4. And this is equal to 3 times the cosine of pi over 12 plus 2 pi plus I times the sine of pi over 12 plus 2 pi. And this is equal to 3 times the cosine of pi over 12 plus I times the sine of pi over 12. So this gets us back to the complex number that represented the fourth root of z when k was equal to 0. So k equal 4 returns us to the case k equals 0. Okay, so now things start to repeat. So if we keep on increasing the value of k, we look at k equal 5, then we're going to get the complex number. We're going to find that when k is equal to 5, that gives us the complex number that we got when k was equal to 1, which was 3 times the cosine of 7 pi divided by 12 plus I times the sine of 7 pi divided by 12. And so things now repeat. So we end up with four distinct fourth roots of the number z. Okay, and so I'm going to stop here and let you do a few of the homework exercises. Oh no. Oh no. How did that happen?